Hi guys, in this video let's look at the Claisen condensation, a reaction that takes place with esters. And this reaction will give a beta-ketoester as product. We will see that. Let's start with a symmetrical Claisen, which involves reacting two equivalents of the same ester. If you take this ester and react it with a base, very often we're going to require some heating here. We can get a new product, and it will be a sort of a dimer type product, two molecules reacting with itself, if this is the only thing that's here. Now the base can do two things. It could add to carbonyl, electrons up, eventually back down, kick this off. But we would not get anything new because we're going to use a base that matches the leaving group here. And so addition, elimination to the carbonyl would not give a new product. The base could also deprotonate alpha to the carbonyl. And I'm just going to show that. We know mechanism for that. Now the equilibrium is not favored here, but still we can produce some of this. And now what can it do? We're not going to add in like an ethyl bromide or some type of carbon with a leaving group. So what could this carbanion, this enolate carbanion, react with? Well, it could react with another molecule of the ester. And so these electrons could add to this carbonyl. Electrons up. That's going to give, so this carbon bonds to carbonyl, electrons onto oxygen. This carbon, the carbonyl, has a propyl group and a O-methyl. So we just made that bond by nucleophilic addition of the ester enolate, or the carbanion, to the carbonyl of another molecule. Well, there's a leaving group here, and we can reform carbonyl. Now we could theoretically kick off this enolate carbon. That is possible. That would just take us back to the two original reactants here. But we could also kick off, and actually the oxygen is a better leaving group at this point, we could kick it off. And that would give double bond to oxygen reformed and the propyl group there. All right. Which, by the way, is the same molecule as shown here. But we're not done yet. By the way, back over here, we formed that plus methanol after the methoxide took the H. I'm not showing that mechanistic step. There's one equivalent of methanol. I told you we'll make two. We get this product plus methoxide. Well, this product is a beta-keto ester. one of these compounds with CH or CH2 between two carbonyls. This H here is fairly acidic. And the methoxide leaving group will take this H, leave electrons behind, and that will give that plus another methanol. When I say that, it is now an anion. Because the pKa here is about 10 to 12. pK of methanol is 16, which is favored. 12 or 16, well, 16 is favored, the weaker acid. So this is favored, and this is how the product will exist at the end. Basically, the product is acidic enough to be considered acidic. And under step 1 is under basic conditions, so this should exist in the basic form. We have to have an H plus workup. An H plus workup, we throw in some hydrochloric or sulfuric acid, etc., whatever your favorite acid is. It's got to be more acidic than water. Water's not going to protonate this because the pKa of this is below 16. It needs to be acidic. Then we can get our final product, a beta-keto ester. This is called a Claisen condensation. All right. Now, usually condensation implies we make water and it's condensed out. Here we're making a small alcohol and it can be condensed out. For example, the boiling point of methanol is about 65 degrees. If you do this step 1, you know, at 100 degrees or so, depending on what actual solvent you use. But if the reaction was at 100 degrees, the methanol, as it's formed, would distill out. And you can condense it with a condenser, and you could call it a condensation reaction. Okay, that was a symmetrical Claisen. We can also do what's called a mixed Claisen. Just like with mixed aldol, we now can have two different reactants. We typically, though, do need to have some reason for selectivity. Otherwise, one ester could react with itself, another molecule of itself. This is going to be a mixed Claisen. With sodium methoxide, we would deprotonate. We would remove the most acidic H. There are no acidic H's here. Here we have acidic H's between the two withdrawing groups, and we can make anion here. Now this carbanion can react with the other ester. By the way, we used ethoxide, so if the ethoxide added to this carbonyl, or that one, electrons up, back down, we would not produce anything new. If ethoxide replaces ethoxide, it's no different. And this would attack carbon. Electrons move on to oxygen to become anion. That carbon has a phenyl and an O-ethyl. Then electrons back down, kick off the O-ethyl, and CN. Reform carbonyl, and there. And that's your final product. We will need H plus workup because the ethoxide will take this H, we'll do the same as above. Okay, and actually we didn't note this as above. We actually need 2 equivalents of base needed. One is to deprotonate the original ester. Okay? It's not catalyst, it's never reformed. Hold on, we did reform methoxide here. No. I'm not going to say 2 equivalents of base needed. Full equivalent needed. It's not a catalyst. If the reaction stopped here, it would be catalyst. We reformed it. But at this point, that takes an H. This is consumed by reacting with the acid. Okay, I hesitate calling this an acid, but it's acidic enough. Okay, it is the acid in this acid-base reaction. Okay, and at the end of step 1, we do not have methoxide, we have methanol. And so to do the reaction again, we need another molecule of sodium methoxide. You need a full molar equivalent of sodium methoxide. It is not catalyst, it is not reformed, it is consumed here. Okay, same thing here. You need a full equivalent of the sodium ethoxide. But we do need to have the H plus workup. But once we go through this process of deprotonating and reprotonating with workup, it's the same product. Okay, there's your product. Now the selectivity here is not always great. It often can be. There's some practicalities that can make it more selective. For example, using excess of this ester. But it is possible for this anion to react with another of itself. I mean, why not? But if it does react with a different ester, it would be called a mixed Claisen. And it's certainly possible to do that. Why don't you try this one here for homework? Okay. Now we can also do like an intramolecular aldol reaction. We can also do an intramolecular Claisen condensation. And down here, treat this with base, we're going to make an enolate carbanion. What can it attack? Well, it can attack right here. Okay? Show the product that would be formed here. Now, an intramolecular Claisen goes by a different name. It is called a Dieckmann condensation. It's kind of interesting or unique where the intramolecular version goes by a different chemist's name. All right. Please show product there. Need to just think mechanistically. Should be pretty straightforward. All right. Here is another example of a Dieckmann condensation. Where we're going to make enolate carbanion, and what could that carbanion attack? Here we're doing acid derivative chemistry. Okay. Here the carbonyl that's being attacked has a leaving group, and so we will reform carbonyl, where in the aldol reaction the enolate carbanion is attacking an aldehyde or ketone, and there's no leaving group here, and so we cannot reform carbonyl. And instead, that oxygen is just protonated, and it's eventually lost as water. So that's more aldehyde ketone chemistry. Okay. Now the next topic is very important, and it's a little bit more in depth than, for example, what we just did with the Claisen and Dieckmann. It's also now Roman numeral 3, but the conjugate or so-called Michael additions to alpha-beta unsaturated carbonyl compounds. These tend to be very reactive. Here's an example of one. Alpha-beta unsaturated carbonyl. Now, some introductory material. If we have one of these types of compounds and a nucleophile, the nucleophile could add directly to carbonyl. We've been doing such for a couple of months now. And that would give this product here, or this intermediate. That's called a direct addition to the carbonyl. It's also called a 1,2 addition, where if we consider this the one carbon, the electrons end up on the next carbon, which is the next atom, I should say. So 1, 2. The electrons end up on the second atom away from where the nucleophile attacked. And in this case, we have some type of proton source, and we can get such a product here. Nothing really new there. What's new in this chemistry is that the nucleophile could alternatively add to the beta carbon, not the alpha, but beta, and move the electrons onto this carbon. And that would give this bond formed and lone pair now on the alpha carbon. But this is an enolate. Okay. Now with some H plus source, we just protonate the carbanion, and we can get this type of product here. Okay. So we have nucleophile added to beta carbon. And this is known as a 1,4 addition, because if the nucleophile adds here and we consider that 1, the electrons end up, well, hold on. Where did the electrons end up? Well, if we consider resonance structure here, electrons here, pi bind up. If we consider this, which is the major resonance structure, and which is analogous to having oxygen anion here, if we consider the oxygen anions, the nucleophile added here, if that's 1, the electrons end up not 2, not 3, but 4. And it's called a 1,4 addition. But 1,4 additions go by the name of Michael additions. Also called a conjugate addition, because the double bond is conjugated with the carbonyl. We're not adding directly to the carbonyl, but we're adding to a conjugated pi bond. So two alternative reactions that can take place with an alpha-beta unsaturated carbonyl compound. Now some information here. The 1,2 product is typically the kinetic product. It's formed fastest and thus always first. The 1,4 product, okay? The 1,4 product is where the nucleophile is added to the beta carbon. It's typically the thermodynamic product, largely because it still contains the carbonyl. The 1,4 product is favored if equilibrium can be established. But equilibrium can only be established if the 1,2 addition is reversible. Remember, the 1,2 addition takes place first because it's fastest. Well, the 1,2 addition can only be reversible if the nucleophile can in turn act as a leaving group. Now we will show examples of what I am talking about here and refer back to this as we move ahead. All right, it doesn't mean that much to you right now. It becomes a reference that we refer to a little bit later. A note here, Michael, full name was Arthur Michael, an American-born chemist, actually studied in Germany under both Hofmann, if you remember Hofmann elimination, and also Bunsen, who created the Bunsen burner. I believe Michael, if you look at some of his biography, it talks about how when he grew up, his father built a chemistry lab for him at his home. Perhaps I think his father may have been a pharmacist. Not sure if I remember that correctly, but it seems like I remember Michael having a chemistry lab growing up at his house. Okay, we can compare this. All right, this is only going to take place if the double bond is conjugated with a carbonyl or some other type of withdrawing group. The double bond has to be polarized. Okay, the resulting anion here is stabilized, all right, by resonance. And that is the only reason we're able to do a nucleophilic addition to an alkene. You cannot do a nucleophilic addition to a standard non-conjugated alkene. And it needs to be more than conjugated. It needs to be conjugated with like a carbonyl, electron withdrawing group. Okay? If you remember in organic 1, we talked about putting anion. When did we talk about that? Anion, no. No, we talked about that in organic 2. All right? Yes. Nucleophile is not going to displace this because the resulting anion, while it is resonance stabilized, it's not delocalized to a heteroatom. Okay? But if we put a strong electron withdrawing group, ortho or para, to the potential leaving group, we can get this. And importantly, this, which by the way looks like an enolate anion, can be delocalized the negative charge can be delocalized to the oxygen, and that allows the reaction to take place. All right? Very analogous here. Does not take place here. Even if it was some alkenes here. The reason it takes place here is because the resulting anion can be delocalized to a heteroatom. All right? Now, by the way, we always add to the beta. We would never add the other way. Okay? Nucleophile will not add to the alpha carbon. That would move electrons here. And we would get carbanion there. But this carbanion is not resonance stabilized with the carbonyl. It's not an enolate. Now, of course, there are lots of compounds that have 2 carbonyls. And in this case, you could add to either one, because this carbon is actually beta to this carbonyl, while that one is beta to this carbonyl. And no matter which carbon you add, you get the same product. If it's a symmetrical, this would be called a 1,4-diketone. Okay? But if there's no carbonyl over here, you're not going to do this because this carbanion is not resonance stabilized. Okay, I'm going to end here with this video. We will pick up, and what we will look at is different types of nucleophiles. Okay? Including like Grignards or amines. And how do they add, okay, to this type of compound? Because some can add 1,2, while others may add 1,4. And we'll see products, okay, and we'll refer back to this information I gave here. Okay. Can also look to make superglue or understand the chemistry of superglue. All right. So we'll pick up with the Michael reaction, Michael additions, in the next video.